Okay, let's have a look at the second weekly test that you guys have just done. I've finished marking it. I think certainly with this first question, it was a mix of between maybe half the class kind of getting it and the other half not knowing what was going on. So with the 1,3-dicarbonyl compound, the hard part about this is recognizing that and remembering that these diesters, or if it was the acetoacetic acid synthesis, this was the diethyl malonate synthesis, that a decarboxylation step happens. And to recognize that this is the bond that is formed in the reaction. And so our electrophile must be this with the bromine on it. A lot of people forgot, of course, that there is another substituent there. Don't forget about it. So this would alkylate that nicely, but then we have to do decarboxylation, which is this two-step process. The base that we need to use, because it's a 1,3-dicarbonyl, we can use a very weak base. Don't be going using LDA with that. It's way too much of an overkill, and no one would ever use LDA in a structure like this or a compound like this in order to deprotonate it. So sodium hydride would have been fine. First step, the base, it could have been sodium hydride, or even to match the OET, say sodium ethoxide. Would have been okay as well. And then we would have added at the same time the electrophile, which is the benzyl bromide derivative. Okay. Step 2 in this process was then the hydrolysis of the ester. So we have now at this stage we would have alkylated OET, and so step 2 is the hydrolysis of that. So that's removing the OETs using sodium hydroxide, and then step 3 is the product is the decarboxylation step, and then we must use acid and heat it up. Generally speaking, so this would have been 4 marks if you got that correct. This one was an aldol reaction. Pretty much like we already covered in class. It was the recognition that this double bond over there, okay, is the one that has formed. There was as a dehydration after the aldol reaction. So in doing that, we've had it's the aldehyde. Again, not forgetting that the chlorine is there. The chlorine was not. There's no OH there that was changed to chlorine or something like that. It was part of the starting material. Okay, we don't change OHs on aromatic rings to chlorines using HCl. It's very difficult to do that. And then this part of the ketone looked like that. And this works because the aldehyde is non-enolizable. Okay, there's no alpha protons to it, and this ketone over here has only one set of enolizable protons. So when it forms the enol, it can react with this, and then the elimination reaction occurs after that, and that gives us this product. That's what we covered in Wednesday's lecture. And then finally, I did mention to you that we were going to do a mechanism of a silyl enol ether formation. I presented it slightly differently, and I had a suspicion this was going to confuse a lot of you, and it did. Remember, I did tell you in class that these reactions are typically done in dichloromethane. Dichloromethane, CH2Cl2. So a lot of you thought that this was a reagent, but it's not. It's just a solvent in the reaction. And the critical thing, which to be fair, I'm glad a lot of you got right, was that the first step is where the lone pair of electrons of the ketone are trapped by the silicon, and we kick out the chlorine group over there. So the initial product, or should I say intermediate, is SiMe3. Okay, now there's a plus there, and there's a methyl group. Now, a lot of people got this wrong. They were drawing this out as OMe3 Si. Okay, and so this of course is wrong, because the O is not bonded to the methyl groups; it's bonded to the silicon. Okay, so just take note of that. That's fairly important. The next step is that because this is done at room temperature and we're using a weak base, triethylamine, while it's true it's a bulky-ish base, it's actually very weak. And so this reaction is under thermodynamic control. And so the base is going to remove the proton at the more hindered side to give the most stable or the most thermodynamically stable product. So ET3, okay, picks that up. That goes in there, and those electrons, flow of electrons to where they are meant to be, and we get our silyl enol ether O, silicon Me3, perfectly neutral. And if we wanted to, we do have a Cl minus, but we've got an N plus because it's 3 ethyl groups and a proton. It's just the hydrochloride salt of that. Okay, so that's all that was.